Yeah, before we start that, let's look at the key limitation of these approaches. Well, the key limitation for subspace clustering algorithms is basically, if you want to apply monotonicity, we need typically density-based approaches with a fixed density threshold. And we talked about that last week, that this fixed density-based threshold is a very hard limitation, because we have to somehow judge high dimensional, like 10 or 20 dimensional subspaces in the same way in terms of density as, say, a 3 or 2 dimensional subspace, which doesn't make too much sense if we look at all the cursive dimensionality stuff, yeah, with increasing search space, increasing data space especially, and stuff like that. So here the key limitation of top-down subspace search is exactly the point that we stressed in the challenges chapter, that we have this kind of circular dependency of what are the relevant features and what are the cluster members. To know about or to determine the relevant features of a cluster, we should know the cluster members, right? But in order to determine the cluster members, we should know about the relevant features. So there is a vicious circle or a circular dependency between those two things: subspace search and cluster search. So the question is how to overcome that. And most of the approaches typically rely on a specific assumption, which we call the locality assumption, to overcome that. And that is actually the key limitation. So the locality assumption is the following. We assume that the subspace preference, which we try to learn in all those methods here. So the subspace preference can be learned from the local neighborhood in the d-dimensional space, in the entire space. Yeah. So the subspace preference of points or of clusters, basically the subspace in which the cluster relies on, or in which the cluster exists actually, this subspace preference is learned from local neighborhoods in the entire feature space. Wait a minute, we talked about clustering in high-dimensional spaces is basically limited by the fact that we have the cursive dimensionality. Distances are not meaningful anymore. We don't have any patterns in the high-dimensional feature spaces because the distances are not meaningful anymore. And the consequence is that, of course, also neighborhood, the concept of neighborhood gets unstable. Recall the concept of stable neighborhoods, and it's kind of problems in high-dimensional feature spaces. Yeah. So the subspace is usually learned from the local neighborhood of cluster representatives or members in the entire feature space. Yeah. So in cluster-based approaches, the local neighborhood of each cluster representative, like a mean or a medoid or whatever, is evaluated, but in the d-dimensional space to learn the correct subspace of the cluster. So we need to rely on distances and neighborhoods in the entire feature space, which we basically said that doesn't make sense, and we basically motivated all that stuff here by the fact that doesn't make sense, and now we use that actually. So that is basically the key limitation of these approaches. Yeah, and the same holds true for these instance-based approaches, because here again the local neighborhood of each point is evaluated in order to learn the subspace preference of this point. Yeah, so this locality assumption is just about to break this circular dependency between subspace determination, subspace learning for clusters or points, and cluster membership assignment. Yeah? And we have to do something to overcome this limitation, and this is the usual way to do that. While random search approaches typically do not suffer from this locality assumption, because they don't rely on neighborhoods or stuff like that. But of course, they rely on sampling, and very often they usually need a lot of sampling rounds in order to produce some meaningful or reliable, or at least non-frustrating results. Yeah? So all these approaches here, the first two have the locality assumption limitation. The third one here, random search, is typically limited by the fact that we typically have to sample a lot of points in order to get satisfying results in that case. Yeah, so just that is the big picture here. And we'll start off with a couple of different algorithms just to show you how these general procedures, general paradigms are actually implemented. Yeah, so that is the basic big picture here. Once again, the different ways here to search for the right subspace, the correct subspace, and the key limitation of these different ways. Yeah, and now let's have a look at the different approaches here. So we first start with ProClass, which is actually a variant of k-means, trying to integrate these top-down subspace search into, or subspace refinement into k-means. Yeah? And or k-medoid in that case, but that's more or less the same. But anyway, and in that case, it's a cluster-based approach, a cluster-based subspace approach, meaning that we look in the local neighborhood of the cluster representatives in order to determine the subspace preference of each cluster representative, actually. Yeah? So it's a cluster-based top-down approach. We'll learn the subspace for each cluster or from the local neighborhood of cluster representatives. And the cluster model is a partitioning-based cluster model. In that case, a k-medoid cluster model. Yeah? So clusters are represented by its medoid, and for each cluster, a subspace of relevant attributes is assigned. Okay, yeah, and each point is then assigned to the closest medoid, where the distances to each medoid the distances are computed based on the corresponding subspace of the medoid. Yeah, so for assignment of points, we use the relevancy of the attributes. So the attributes that are not relevant are just weighted by 0. Yeah, so they are excluded from the computation of the distances, and only the relevant attributes are actually considered for computing the distances between points to the nearest medoid. And then the authors, the method also tries to normalize these distances in order to make them comparable, of course, because we may have, I don't know, a 4-dimensional subspace cluster and a 10-dimensional subspace cluster. If we don't normalize the distances, then we have, of course, distances in a 4-dimensional space and distances in a 10-dimensional space. And of course, in order to somehow compare them, we need a kind of normalization in that case. Yeah, and we also have here in this model a kind of model for noise. So points that have a large distance to their nearest medoid or medoids are classified as noise. Makes sense in that case because we argued that in high-dimensional spaces we may have a lot of noise and stuff like that. So and of course the traditional k-medoid or k-means model has to assign each point to exactly one cluster. So in that case, it probably makes sense to somehow change that a little bit or extend that a little bit, and also allow outliers or points to be classified as noise. Yeah? And we just have a distance threshold here that says that if the points are not closer to their closest medoid than this threshold, they are classified as noise.